Get ready for some moon magic here on the Reflector channel. I'm going to show you how to capture stunning 3D images of the moon, and not just one way, but 3 different ways. Now, even if you're new to the hobby, there is a method here for you. So buckle up and let's dive right in. To make 3D pictures, you're going to need 3 different ingredients. Now, the first thing you need are a couple of cameras like these. Or if you just want to use eyeballs, you can do that too, preferably your own. Second, you're going to need to place the cameras about 3 inches apart. And of course, third, you have to have something interesting to point at that is about 65 feet away or closer. Now, I'll get to why that number is important here in a moment. When you have such a setup, each camera will take a slightly different image, like these. You have one on the left and a slightly different one on the right. Now, your brain takes these 2 slightly different images and it puts them through a process called stereopsis. Now, what that does is allow you to perceive objects at different distances along your line of sight. That slight difference in the images is sometimes called parallax. Now, the farther apart your eyeballs are, the more amplified that parallax effect is. It's that angle between your eyeballs and the target that becomes very, very important, especially in today's video about the moon. When we look up at the moon, we see a 2-dimensional view. Now, why is that? Well, it's because the moon is so far away that the parallax angles are actually considered almost parallel. That means that each eye is fed the exact same image. In this case, that stereopsis process fails, and we end up with a flat 2-dimensional image. So that begs the question of how close does an object have to be before we can see it in 3 dimensions with our own eyes? Or more importantly, in this particular video, how far apart do your eyeballs have to be in order to see the moon in 3 dimensions? Most of the research that I could find showed that the distance judgment that's based on the parallax angle starts to fade after about 20 meters. That's roughly 65 feet. Beyond that, our brain uses additional visual cues such as relative object heights, like think of telephone poles getting shorter the farther they are away. Or we move our head to amplify that parallax effect. Now, using 65 feet as a benchmark, that puts the minimum parallax angle at about 1/4 degree. And that's a pretty small angle, but the angles are about to get even smaller. The moon is roughly 239,000 miles away. That works out to about 15 billion inches. Now, if you draw up the triangle and you do the math, that means the angle between your eyes and the moon is about 0.000000114 degrees. Now, I might be off by a decimal point, but it's very, very small. And that's a lot less than 1/4 degree. In fact, it's so small that we really see the moon as a 2-dimensional disk, as I mentioned earlier. Now, that distance becomes more believable when you see it laid out to scale. And you see just how far away the moon really is from the Earth. And here it is. The moon is shown here at about a distance of about 30 Earth diameters away. To say it is far away is quite the understatement. So with that, are 3-dimensional photos of the moon even possible? Well, of course they are, especially here on the Reflector channel. If you want to reach that minimum angle of about 1/4 degree, the distance between your eyeballs has to be around 1,000 miles. Now, if I set up a camera in Phoenix, Arizona, and another one here in North Texas, and both cameras took a picture of the moon at roughly the same time, we would have enough of that parallax angle to see a 3D moon. But I don't know anybody who lives in Phoenix, Arizona, so let's move on to the next method. The second method would be to take a picture of the moon, then hop on a plane and fly at 500 miles per hour for about 2 hours, and then take another picture of the moon with its slight angular difference from where you were when you first started out. Now, for all you keen observers out there, this would only work if I flew east, because if I flew west, I would be fighting the Earth's natural rotation that is carrying me back to the east at a pretty good clip. In fact, at the equator, the tangential speed is at around 1,000 miles per hour. That very speed boost is why most rocket launch facilities are located as close to the equator as possible. It gives you basically free launch velocity. All right, so okay, this is starting to turn into an SAT math question. So is there a simpler way to take a 3D photo of the moon? You bet there is. If you're enjoying this video, please gently push that like button. Don't smash it like other people do. Be nice to that like button. And also, if you want to see more videos like this, push subscribe. Thanks, it means the world to little channels like this. Now, I've already alluded to the fact that the Earth is rotating under the moon. We here on Earth rotate once every 24 hours, but the moon takes a lot longer, just under 30 days to make that complete trip around the planet. This means that we are spinning pretty fast relative to the moon. In fact, over a single evening, our angular view of the moon will change ever so slightly, just due to our travel here on the Earth. Now, this change in perspective actually has a special name. It's called diurnal libration. It is said that during the night, the angle sweep is about 1/2 of a degree, depending on where you are viewing it from on the Earth. So here's how it works. First, you take a picture of the moon, and then you just sit around for a while resting. Maybe read a cool adventure book about Mars. I'll put a link to a really cool one in the description box if you want to give it a try. While you're doing this, the moon zooms overhead, and when it's all done, you take another picture. Now, if you compare the two photos, you'll see a slight angular difference, which is exactly what you need to construct a three-dimensional photo. Now, I should mention that this three-dimensional effect works no matter what phase the moon is in, but a full moon will probably produce a stronger effect. Now, the time required will differ on your latitude, so feel free to experiment. If you're at the North Pole, don't even bother. Sorry, Santa Claus, you're stuck seeing a two-dimensional view of the moon. For me, 2 to 3 hours is pretty good to start generating that 3D effect. And now I present to you the lazy man's three-dimensional photo of the moon. Now, to see this in 3D, place your thumb in the middle between the two images and focus on your thumb and move it towards your nose. You should start to see a third image show up in the middle. Quickly get your thumb out of the way and try to focus on that middle image. Hopefully what you're seeing is the moon as a three-dimensional curved surface, especially out towards the edges. I find looking at the craters on the top and the bottom produces a really neat effect. Now, I want to know if you can see it. Please leave a comment down below if you can see this 3D effect. And if you don't know how to attach a smartphone to your telescope, well, you'll want to watch this very short video that shows you step by step how to do this with any smartphone on any telescope. Thank you for watching, and clear skies.